Hello again, welcome to another lesson in geometry. Today we are covering section 9-6, compositions of reflections. Alright, so we write T for true or F for false for our review here. So we have some vocabulary. Our first one is a reflection flips a figure across a line of reflection, and this is true. So if you have a square, A, B, C, D, we could have a line of reflection. When we flip it over, we'll have a new square over here. Same size, so it'll still be congruent. Okay, but we flipped it around, so this will be A prime, B prime, because B is closer to the line of reflection than A was, and then C prime and D prime. All right, so reflection turns the figure about a point. This one's definitely false. Remember, this is actually a rotation does this. Okay, a reflection's pre-image and image are congruent. This is true. All reflections, rotations, and translations are isometries, remember? And isometries just make new shapes that are congruent. The only one that changes to make similar shapes is a dilation. All right, so the orientation of a figure reverses after reflection. This is true. You can take a look at this square here. Originally, it's going A, B, C, D in clockwise order, but now it's going A prime, C prime, B prime, C prime, D prime, and counterclockwise order in the image. So the pre-image and the image have reversed orientation. Okay. So a line of reflection is horizontal or vertical. This is false. We don't just have to reflect across horizontal and vertical lines. We can reflect across any line. Okay. All right. Vocabulary builder down here. We have composition. Okay. Other words for composition are compose, composite, and another one, composite as a noun. So our definition here, a composition combines parts. So math usage here, a composition of transformations combines two or more transformations in a given order. And usually the order matters. Okay. All right, so complete each statement with the appropriate word from the list and use each word once. So a first one is a composition of reflections has at least one line of symmetry. Now we did not have to learn about symmetry in our standards, so you can kind of ignore this, but a symmetry just means there's some line that you can flip the shape over and it'll be the same on both sides, and it'll still match up. Or, and let me try to explain that a little better. So here's a triangle, isosceles triangle. If I flipped it through that line of reflection, it would still match. Okay, or there's a rotation of 180 or less that will get me back to the same shape. Okay, all right, so you can make any figure congruent onto another using a composition of reflections. So if you think about it, if we had the square like before, if we flip it once, it reverses. If we flip it again, it's back to the same orientation. Okay, so a composition of rotations is always a rotation. If you spin it 80 degrees and then you spin it 20 degrees, it's the same as if you spin it 100 degrees. So you don't have to do those two separately. Okay, all right, let's flip it over and see what's on the second page. Okay, at the top of page 2, we have two theorems here. We have theorem 9-1 and theorem 9-2. Now, they kind of go together though. So theorem 9-1 says a translation or rotation is a composition of two reflections. So what it's saying in this one is that we don't actually need translations or rotations at all. Any translation or rotation we want to do, we can accomplish by just using reflections. Okay. All right, so then theorem 9-2 explains how that works. All right, so our first one is a composition of reflections across parallel lines is the same as the translation. Gets the same result. So if we have this pre-image over here in red, and we could translate it, they're translated along that red dotted line here, and they end up with this image over here in blue. And what this theorem says, the first part here, is that instead of doing a translation, you could just make two parallel lines, each one at 1/4 of the way between the red and blue, and the other at 3/4 of the way between the red and blue. Okay, and then if you do reflections over those two parallel lines, a composition of reflections, you'll get the same result as if you did the translation. All right, so let's see how that works. So if I take the red one and I reflect it over the first green one right here, I end up with this. Okay, this new triangle. Its orientation's been flipped because we did a reflection. All right, so we flipped it over a line of reflection 1/4 of the way between the red and blue. And then we're going to flip it one more time with the 3/4 of the way between the red and blue line of reflection. Okay, so we moved the red one, we flipped it, we got the black one, which is halfway in between, and then we're going to flip it one more time, and we end up on the blue one. So it's the same, two reflections are the same as one translation. All right? And then our second part of the theorem tells you how you could do a rotation. So a composition of reflections across two intersecting lines is the same as a rotation. And notice it doesn't even say that the lines have to be perpendicular here. Okay, so we just have to find two intersecting lines and make it work. Okay, so for every rotation, so in this case, we are rotating around point in the middle here. So we rotated it, we end up there. If we made some lines that cross, okay, at that part, then we could make that same rotation happen. So the first thing they do is they reflect it across this line, and they got this image up here. And then they reflect it across the second line, and they got this image, which is the same as if they had rotated around that intersection point in the middle to begin with. Okay, so we don't need rotations, we don't need translations, we just need reflections. But the problem is, to see reflections, to make them do all those things, it's hard to come up with all the lines every time easily. So we shortcut it. We say, oh, we can slide it, we can rotate it. But in actuality, we're doing only reflections. In problem 1, we have composing reflections across parallel lines. So this just gives us a little practice about doing this. Okay, lines L and M are parallel. So down here on this picture, we are already given that L is parallel to M. And we want to know what is the image of R. So R was just a letter in the middle here. Okay. Reflected across line L and then across line M. So first we want to reflect it over line L, then we want to reflect it over that reflection over line M. Okay, and we want to know when we are done, what is the direction and distance of the resulting translation? So those are the questions we're going to answer after we do our reflections. All right. So they don't actually label this point, but there's supposed to be a little point P on the bottom of R here. And then it shows you where that should go over here when we do our first reflection, and it shows you where that point should go when we do our second reflection. All right, so let's give this a try here. All right, so first thing we do is reflect R across, the first thing we have to do is we would draw in a dashed line perpendicular to L and M that intersects L at point A. Okay, so it's saying, hey, go ahead and draw this dashed line to help you with your reflections. Okay, and it will also show us the answers later on, help us find our answers later on. Okay, all right, so we have that dashed line in there, and complete each step to show the composition of the reflections. Remember, a composition of reflections is just two or more reflections put together. Okay, so the first thing we're going to do is reflect R over LM. So we could just freehand this in here, and when you're done, it should look a little something like this. Okay. All right, so remember, R is going to change its orientation, so it's going to be flipped around. And the point of where P was touching, so it's still touching, but the leg of R got flipped up a little when it turned around. Okay, so now the R is kind of leaning over. All right, and then our second job is to reflect the image that we just got across line M. So we're going to do a far reflection, and it says that we could use P double prime to help us. And when we do that reflection, R is going to turn back to the same orientation, and the leg of R, the straight leg of R, is still going to be touching P prime, P double prime. All right. Underline the correct word to complete each sentence. So our final thing was a translation to the right along the dashed line. So that's answering what is the direction. Okay, so what we really did was we just picked up R from here and we translated it down that red dashed line to the right. Okay, the direction of the translation is parallel oh, no, not parallel to L and M, it's parallel to AB. It's perpendicular to lines L and M. Okay, so we followed along the perpendicular one, and that was perpendicular to L and M. So our direction is perpendicular. Okay. All right, so use the justifications now to answer. Our second part is, what was the final distance? So how do we get that distance? All right, so they did put some A's and B's in here. So we're going to use those now. They didn't seem important before, but they are now. So this is point A, this is point B, here's point P, here's P prime, and here's P double prime. And our job is to figure out the distance from P to P double prime. That's what we wanted to know. And we know that that distance is going to be the distance from P to B plus the distance of B to P prime, P double prime. And that's just saying that this little distance here plus this distance makes the big one. So the segment addition postulate. Secondly, we know that we could replace this guy, so we could do something like this. P to B is the same as B to P prime. All right, so how does that work? All right, so we still have the P to B segment. I'm going to do it in green this time. And they're just saying that, hey, the B to P double prime is the same length as the B to P prime, okay? Because it's a reflection over the same line. We reflected P prime over line M to get P double prime. Therefore, P prime and P double prime should be the same length away from B. So that's why we can replace B P double prime with B P prime. All right. Then we copy down the PB again. We're not doing anything to that yet. And we're going to replace BP prime with this thing. All right, let's show how that works. That means I'm going to say that this whole green one, that's I just did in red again, is going to be replaced with three little segments. We're going to replace it with BP, that piece. We're going to replace it with PA, that piece, and AP prime. So we broke this segment BP prime into three parts. So once again, we use the segment addition postulate. All right. Now, we keep bringing down that PB. But now we're going to do something in here. We're going to bring down this BP, put it right there. But these two guys are going to turn into this. Well, how does that work? All right, so A and P prime are exactly the same length because they are the same distance from line L. That's what our line of reflection told us to do. Okay, so we can just replace it with two of PAs. All right, so now we have 2 times BP because we had two BPs in there. PB and BP are the same. All right, and plus 2 PAs, and then we can factor out the 2. All right, and then for our last step, we get this to be 2 times, well, let's see, this is a segment addition again. So BP and PA, we'll just cut out the middle guy here, and that's the same as A to B. It's going from A to B. All right, so the resulting translation moved R a distance of 2 times AB. Now, what did that mean? Let's look back at our picture. Okay. Do a little bit of this, okay? So AB was the distance between the two parallel lines we were reflecting over. And we moved R 2 of those distances. So this distance here was the same as this distance twice, same distance twice, okay? That's how far we moved it. All right, now it's not the same for everyone, so it's just letting you see how these reflections, composition of reflections work. All right, let's flip it over and take a look at page 3. All right, on the top of page 3, we have theorem 9-3, the fundamental theorem of isometries. So remember, isometries is moving an image and pre-image are going to be congruent to each other. So we can move it around, but it's going to stay the same size. The orientations might be different, though. So in a plane, one of 2 congruent figures can be mapped onto the other by a composition of at most 3 reflections. Okay, and this makes sense because we might need 2 reflections to do a translation, okay, to get the shapes near each other so that we can do a third reflection to flip it back over. But the two reflections that we do for our translation, or even a rotation to reflections, is going to flip our composition. So for instance, if we started with a little triangle this way, and we knew we had to end up with it the other way, the other orientation, okay, then we're going to need to do 3 reflections, okay? 2 reflections is going to get me my triangles near each other somehow, where I can then do a third one to flip it on top. And if we think about it, that makes sense, because every time we do a reflection, we're going to change the orientation. So if I do my first reflection, it would look like that. Okay, my second reflection is going to flip it back around, but I want my final one to be back here, so I have to do a third one to get its orientation back around. Okay, so if I know that they're going to end up being congruent and their orientations are opposite right now, then I'm going to need an odd number of reflections to make this work. So if figures start off with opposite orientations, then I'm going to need either 1 or 3 reflections to make it work. 1 reflection if we can reflect it directly and get right on top, or 3 reflections, and the first 2 reflections are going to be either to do a rotation or translation, and then the third one's just going to be to change the orientation. So problem number 3 says find a glide reflection image. So a glide reflection image is just a composition of a translation followed by a reflection. And we're asked to use this formula for our translation and use this line of reflection for our reflection. All right, so first off, number 14, they break this into some parts here. We're going to do the translation. So the translation just says add 1 to all the x coordinates and leave the y's the same. So let's go in here and put add 1 to our x coordinates, leaves the y's the same, so 2, 3, and 1 stay here. So our first one is -4, 2, and then 0, 3, and then -1, 1. All right, so we'll go ahead and plot that. So -4, 2 is right here. That just slid t 1 spot to the right. 0, 3 is right here. So that's slid E 1 spot to the right. And then -1, 1 is right here, and that slid X 1 spot to the right, which is what our translation was supposed to do. And then it says in a reflection across a horizontal line, only the, well, what's going to change? Which coordinate? So going over a horizontal line is going to leave the X coordinates the same. It's only going to change the Y coordinate. Okay, and that's because we're flipping it up and down, so the left and right of the points stay the same. All right, so find the vertices of the triangle you graphed in exercise 14 after the reflection across y equals -2. So this is going to take -4, 2, and it's going to move it down. So let's do our reflection over here first, and then we'll write it down. So this t was 1, 2, 3, 4 away, so I count 4 down. 1, 2, 3, 4. So 4 away from the line of reflection. So this is going to be t prime right here, and t prime was at -4, -6. Okay, and then E is 1, 2, 3, 4, 5 away, perpendicular to the line of reflection. So we count down 5 again from the line of reflection. So 1, 2, 3, 4, 5, and this will give me E prime. Okay, so E prime is going to move from 0, 3 to 0, -7. All right, and then X currently is 1, 2, 3, perpendicular to the line of reflection. So when I move it down, I'll go 1, 2, 3, and put it here. All right, so let me erase that work in there, and then we'll put X back in the right spot. So right here. All right, we can draw this in now. This is our new triangle. And let's write in that vertice of X. So X moved from -1, 1 to -1, -5. All right. So the image of triangle TEX for the given glide reflection in the triangle with vertices is going to be T prime at -4, -6, E prime at 0, -7, and x prime at -1, -5. All right, so just a quick thing to be careful with. This is true for number 15. It does only change the y-coordinate, but if the line of reflection is not the x-axis, you got to be careful. It doesn't just flip the sign of the y-coordinate. It actually does move the y-coordinate to a whole different place. So just think about that. So for instance, like E here was moved down 5 away, so then it moved 5 away on this side also. Okay, so it didn't change the x-coordinate, but it did move it a total of 10 this time. Okay, all right. Theorem 9-4 on the bottom, isometry classification theorem. There are really only 4 isometries, so there are only 4 transformations that make congruent shapes from the image and the pre-image. All right, so the first one is a translation, keeps the same orientation. Remember, we can do a translation with 2 reflections. The second one is a rotation. It also keeps the same orientation, and we can do a rotation with 2 reflections. And then we just have a plane reflection, just one reflection. This does not keep the orientation, so the orientations are opposite. And then we have a glide reflection. That's a translation followed by reflection. So this changes the orientation to opposite. Okay, the translation part leaves it the same, but as soon as we reflect, we get the opposite orientation. So these are our 4 isometries. So the 4 transformations that leave congruent shapes for the image and the pre-image. Okay, problem number 4 on the top of the 4th page says, each figure is an isometry, image of the figure at the right. Are the orientations of the pre-image and image the same or opposite? And then what type of isometry maps the pre-image to the image? So this is our pre-image. Okay, and for part A, our image has the same orientation. The P is not flipped over, it's not a backwards P, it's just been rotated. So this has the same. And what does a rotation? Oh, well, that's easy. A rotation is the isometry that made it. All right, so this P has the same orientation and is not rotated at all. So this is the same, and this is just a translation. Okay, and then the last P has a backwards image. It turned into a B. Okay, so what did we do to get to that? Okay, that's definitely a reflection. That's the only thing that can flip it upside down. But we're probably going to go ahead and call this a glide reflection because we have to translate it first to here and then do a flip, a reflection. So a glide reflection. All right, so choose the correct words here, the map with this. So first one we said was the same, and the same orientation, and it was a rotation. So same and rotation. The second one was the same, and this was a translation. And the third one was opposite. Okay, and it was a glide reflection. Okay. All right, so our lesson check. So if you reflect triangle DEF across lines M and N, and then across line M, and then you reflect it across line N, your friend says you get the same if you do it in reverse. You do N and then M, and explain your friend's error. So place a check in the box if the response is correct, or an X if it's incorrect. So this is definitely wrong. These lines are not perpendicular. Therefore, since it's not perpendicular, the 2 reflections are not going to put it in the same place. They're going to do a different amount of rotation than 180. So if the lines are perpendicular together, they'll make same as a 180 rotation. So this is a clockwise or counterclockwise. Clockwise rotation has the same image, and this is wrong. So I'm saying, like, if you do a rotation, okay, and you rotate it 60 degrees this way, or you rotate it 60 degrees that way, they're not going to look the same. So your friend's error is the resulting rotation is not in the same direction. And then I'm going to show you a geometric sketch pad to see a little better what's going on. Okay, so the resulting rotation is not in the same direction. All right, so let's take a look at the geometry sketchpad and see what's happening here. Okay, so on our sketchpad, we have the yellow triangle here, and first it's reflected across this line, the horizontal, and we get the pink one, and then it's reflected across the vertical, and we get a purple one that's covered up right now. Or if we do the other opposite way, we reflect the yellow across the vertical, we get this light brown, and then when we reflect across the horizontal, we get the dark brown. Now, right now, these are perpendicular, so they end up in the same place. But as soon as I change this from being perpendicular, you can see what they're talking about, how the images flip a little. Okay, so they don't rotate a full 180, and they are rotating in the opposite direction. So when we flip vertical, then horizontal, or close to vertical and then this diagonal, then we get this light brown, and then it flips up here. So it's rotating around this direction, counterclockwise. But if we flip the diagonal and then the vertical, it comes around here to the purple one. So it goes pink to purple. So we're rotating clockwise in this case. All right. So the closer they are to perpendicular, the closer the shapes will be to the same because we're rotating them in opposite order. So the farther away from perpendicular, the farther the final results will be from each other. Okay. So you can see it rotate. So it's getting closer, and then boom, they're the same when it's perpendicular. So you can see that the brown, the dark brown, is rotating clockwise or counterclockwise, and the purple is rotating clockwise. All right, so when two shapes rotate in the opposite direction, they're not going to be the same unless they both rotate 180 degrees. And the reflections that do 180 degree rotation, the two reflection lines have to be perpendicular to each other. All right, so that concludes our last section of chapter 9. Notice we skipped over a couple in here, so we only need to know about transformations.